So on our previous lecture, we were talking about the system developmental life cycle. Today, we're going to talk about the system development process. And this is lecture 4, part 2. And the material that is going to be covered is also part of chapter 4 of your textbook. So remember, you have access to your textbook through the library. So today we're going to look at the last 2 parts of this lecture, the evolutionary characteristics of development process and the systems engineering method. Okay, so the characteristics of systems evolve through the life cycle. And we already looked at the life cycles, all the 3 stages and the phases within each one of the stages. Some examples of these characteristics include having a predecessor system, system materialization, the participants, and the system requirements and specifications. So on the proposal for the project, one of the things that I asked you to do was to try to come up with a set of requirements that the new system that you're proposing was going to have or have needed to achieve. So we're going to talk about requirements in the next following lectures. In addition to that, having a predecessor system, what that means is that you don't have, every time that you're proposing a new idea, you don't have to build that idea from scratch. You can use a predecessor system as a baseline. So for example, if you're trying to design a new airplane, you don't have to go and create the airplane from scratch. You can build upon the technology that's already available and the systems that are already available, such as airplanes from different companies. System materialization, we're going to talk about that in the next few lectures, and the participants. So the engineering of a new system often starts from having a predecessor system. And what is, as I mentioned, the predecessor system is the system that is currently in place, right? And if you're trying to improve upon that, you're going to use that as your baseline. So what is the impact of this predecessor system? First, eliminating or alleviating the deficiencies of an existing system. It's often the starting goal of a new system. So going back to the example of the car, for, I don't know, many years we were relying on gas engines. So now we're looking at the need of improving in the mileage and need of using different power sources. So a new system could be the development of these electrical cars and also the development of these hybrid systems. Unless the existing system is worthless, the new system is often based on the technologies and architecture of the old, which is again the case of these new engines that are being placed on cars. If existing components and technologies are satisfactory, a new system can incorporate them directly. So, again, using a different example, you're familiar with the systems like the cell phones. Every year you see that there's a new model. Most of the time you have some new parts or some new features in the cell phone, or maybe an improvement of current features, but the actual system is not completely new, right? You're building upon the existing predecessor system. So that's the impact of this predecessor system. You are eliminating the deficiencies of the current system, maybe making it more, giving it more space, or giving it better camera in the case of the cell phones. Again, you are building upon that, and some of the technology that is already satisfactory, you can use that to develop the new system. In terms of system materialization, the development of the system from an abstract need to assemblage of actual components that cooperate to fulfill that need. That's what we call the system materialization. And in this table that is coming from your textbook, we have the evolution of the system materialization through the system life cycle. So if you remember the phases of the system life cycle, those are listed at the top of this table. So you see concept development and engineering development, and we have some of those stages here: the need analysis, concept exploration, concept definition, and then for the engineering development we have advanced development, engineering design, and innovation and evaluation. And on this part of the table we have the level at which each one of these phases will affect the development of the system. So from the system up to the part, or from the part up to the system, how each one of these phases are interacting with the development of the system. So for instance, if we look at the need analysis, which is the first column inside the concept development area, we are affecting the system in terms of defining the capabilities and effectiveness. So we are trying to visualize what should be the performance of this at the system level. Then when we go into the concept exploration, we are also affecting the system, but also we're going lower in terms of that hierarchy. We start thinking about the subsystem that should be part of this new system that we are proposing. So at the concept exploration phase, we are also looking at identifying, exploring, and synthesize concepts. That's at the system level. And at subsystem level, we are trying to identify the requirements and ensure feasibility. Requirements in terms of, okay, so if I'm going to develop this type of system, do I have the technology? And what is the technology that is going to be required? And then we move to concept definition, and we start looking at defining selected concept with specifications. So now, once we have identified some of the possibilities in terms of concepts that we can propose to solve this problem, we start defining the selected concept specification, again at the system level, and then at the subsystem level, we look at defining the functional and physical architecture of the system. And then we go further into the hierarchy. Now we're going to look at the component level, and we start allocating functions to components. So, so for instance, we are looking at a cell phone design, or designing a new cell phone. We said that probably we need to provide some type of new way of charging your cell phone. So if that's the case, maybe you want to rely on the solar energy. So you might find a way to place some type of solar panel into your cell phone, for instance. So that could be an idea of how to translate that function into a component. Functioning in terms of recharging the battery of the cell phone, the component will be the user's solar panel. So how do you transfer the functions that the system has to perform into components that could perform those functions? And then when we get into the engineering development process, we are looking at advanced development. So we want to validate the concept, we want to validate our subsystems, we want to define the specification of the components, and also we want to allocate functions to the subcomponents. That's going a little bit farther in terms of the development hierarchy. And then in terms of engineering design, now we're moving into the specialist area. As you remember, subcomponents and parts are part of the specialist area, not necessarily part of the systems engineering. So now we're looking at the design or make or buy of some of those parts. Are you going to design them because they don't exist, or are you going to be buying them from a supplier? And then finally, we got into integration and evaluation. Here there are three areas at the component, subsystem, and system level. Those belong to the system engineer. We're looking at to test and evaluate. Remember, testing, making sure that you're testing your system on all the possible environments in which you're going to put this system into work. And also integrate a test. So how is this going to be interacting with the existing interfaces of other subsystems or systems that are going to be part of the functionality of this new system. This is also a very good description of how the principal participants in a typical aerospace system development. Here what we're trying to show you is the participant change over time. So at the bottom we have again the major stages of the system life cycle. So we have concept development and engineering development, and you see who is involved at the need analysis phase. We have the systems engineers, the system architecture system, and as we move forward, you see how those responsibilities or resource level are increasing. So again, we have the same, but maybe a little bit more involvement. Same thing here. And then when we get into the advanced development, you see that most of the responsibilities into the system engineer. And then when we move further in the engineering design, you see how the specialists or the design engineers are taking most of the load when compared to the other disciplines. And then finally, we have a more balanced distribution of the work at that last phase. The system representation also changed over time, as shown in this table. So what we're trying to show here, again, we have the system life cycle at the top and their phases for each one of the stages. And we have the document and the system models that are required in each one of these stages of the developmental cycle. So for instance, need analysis, we are looking again at system capabilities and effectiveness. So those are the documents that you have to prepare. You need to understand the problem. You need to understand what is required from the system in order to make it work, in order to make it successful. Some of the system models that you can use, operational diagrams, mission simulations. These are most likely for projects like those that NASA perform, the mission simulations. Operational diagrams give you an overview of, this could be things like flowcharts that will give you an understanding of, okay, these are all the things that I need to consider, like the block diagram that I requested as part of your proposal. These are the people who is going to be other people or the users of the system. So those diagrams will give you an understanding of the items that are involved as part of the system. Concept exploration, we start looking at the system performance requirements. Like here, we want to have, like, again, going back to the car example, we want to have a car that is not relying on gas. Okay, so that's that's the capability. But now we want to go further in terms of, when we go to the concept exploration, we want to state, okay, it's not going to be using gas anymore, but I need to specify the performance in terms of how many miles I'm going to get from this car. If you're looking at an electrical car or hybrid, maybe a hybrid will be a better example because we can compare. So how many miles per gallon? Remember, the hybrid will still use gas. So is that giving you just setting up a goal to reach? Like, I want the hybrid system to be able to give you 40 miles a gallon. You know, that would be a performance requirement that is targeting your system. Another thing could be the vehicle must be designed and taken into production to cost less than $30,000. Right? That's another performance requirement. You don't want to create a vehicle that gives you 40 miles a gallon, but you spend $100,000 or $100,000 making that vehicle. Nobody's going to buy that, right? So we need to specify what are the performance requirements in terms of cost, in terms of the actual performance of the system, and also in terms of the timeline. So how much time do you have in terms of resources and budget? Concept definition. So once you have established those requirements, you can still use the system diagrams, high-level system simulations to come up with the concept. And concept definition, now we move from system performance requirement to functional requirement. So these are the things that the system has to achieve in terms of performance. So what are the functions that are needed for you to be able, or for the system to be capable of performing those? So, for instance, we can have input-output functions. Like if I give the system this input, this should be the output of the system. And here we start looking at the architecture of the product and view simulations and mock-ups. So looking at the technology that is available, how are we going to satisfy these requirements? Do we need to design some new technology in order to satisfy these requirements? So like in the case of the hybrid, he came up with a new type of engine, right? So those are new technology, functional requirements. And in terms of advanced development, system design specifications, so now we get into more details of the size of the engine should be this much. It should only occupy this percentage of the space of the vehicle, and so on. And from there, we move to the design documents. And so we are basically putting everything into writing. So we have documented everything that is part of the system. And then we plan for testing and validation of the system. And that's at the integration and evaluation phase. So system representations change over time, and this is a good table to follow in order to see the evolution of the system representation. Questions? So I'm repeating some of the things over and over again because I want you to be able to see how can you take that into your project. So now you have an understanding of the problem. Now you understand some of the limitations of the systems. In case of some of you that are proposing systems to improve the way that certain things are being done. So how do you take that problem? How do you take that new idea and you develop a system along that line? So let's talk about the systems engineering method. Okay, so there are several systems engineering methods, usually based on an organization. The system engineering method is a systematic application of the scientific method to engineering of a complex system. Okay, so I'm pretty sure that you have heard this scientific method over and over again since high school. So what the system engineering method does is if we try to adapt the scientific method into systems engineering. And we are going to adopt the method that is proposed in your textbook, which has 4 basic steps. The first one is the requirements analysis. And identify what requirements what requirements are needed. Functions definition, translate requirements into functions the system shall perform. And then physical definitions, synthesize alternative for physical implementations. And then design validation, which models the system environment. Okay, so again, I think I mentioned this before. So what we're trying to do now, and you as part of your project, you have a problem, right? You have identified that problem, and you want to solve that problem. This is a problem that has a societal need, and you are trying to come up with an engineered system to solve that problem, right? So you have a problem. Now, what you're going to be doing is identifying the requirements, which was also part of the proposal. What are the requirements? Can you talk about the cost? You can talk about the performance. You can talk about space. You can talk about many things in terms of the requirements. Capacity, size, users, and from each one of those groups, you can come up with different requirements. Like in terms of the user, so this system will be should be designed so students can use it, or this system should be designed so elderly people can use it, or this system should be designed such as maybe you're designing a system for animals, right? So this should be a system that should accommodate the animals that you are designing for. So you're specifying your requirements, you identify what requirements, they should be what requirements are needed. And then from there, you're going to start defining some functions. So for each one of these requirements, we need to specify a function. Okay? Functions, functional definition. So let's look at cost is maybe the most challenging one because you need to understand all of that in order to make sure that you are within cost. So maybe one of the functions is that the system, well, again, let's look at performance. So performance, if you're looking again on a car that gives you certain mileage, so performance will be getting a car with 40 miles a gallon. Then their functional definition can say use renewable energy engine. Okay? Or hybrid energy system. So now you are trying to see how can you achieve that performance. Right? You're translating that requirement into a function. Okay, so translate requirements into functions that the system shall perform. The system should use some type of hybrid energy engine. Now, when we move to physical definition, here's where you start looking at technology. Maybe we can use a hybrid engine from Toyota, or we can use an electrical engine from Tesla, or we can use, so those are physical definitions that can allow you to implement that function. And then finally, so you see where you're going. You understand the problem. You have the requirements. Now I'm trying to say, okay, these are the requirements. These are the functions that I need in order to meet these requirements. And then knowing those functions, I can start targeting some physical implementation, say technology, or software, or a program, or training, you know? What are the tools that you're going to use to make this happen? And that could be, there could be multiple options. Okay, I'm not saying that, okay, so I'm looking for to use some type of hybrid energy system. There's electrical, there's solar power, there's hybrid. So those are alternatives, right? So when you have multiple alternatives, that's good, because what you're trying to come up with is not just with one concept. You want to have multiple concepts, and then based on that, you're going to try to find the best mix of tools that will give you the best system. And that's the concept that you're going to move forward. Okay, so out of all the alternatives, you're going to select one concept that is going to move forward. Okay, so this is kind of an overview of where we are heading. Okay, we want to make sure that we follow this engineering method in order to get that design, that final design, because after that we need to do the design validation. We want to make sure that this is going to perform as expected in the environment that we are going to place the system, and also is capable of interacting with the existing interfaces. So let's look at this step by step. Requirement analysis, again, problem definition. This is what you're trying to do as part of the proposal, assembling and organizing all input conditions, including requirements, plans, milestones, and models from the previous phase, identifying whys of all the requirements in terms of operational need, constraints, environment, other high-level objectives, clarifying the requirements of what the system must do, how well it must do it, and what constraints it must fit, and then correcting inadequacies and quantifying the requirements whether possible. Quantifying meaning that you are putting a number when it's possible. Like I said here, the performance must be 40 miles per gallon. If you can provide a figure, it's better. If you know the cost, the maximum cost that you can spend, then that has to be part of your requirements. Functional definition, translating requirements into functions, actions, and tasks that the system must accomplish, partitioning requirements into functional building blocks, defining interactions among the functional elements to lay a basis for the organization into modular configuration. A modular configuration could be, you can think about trying to think about the subsystems of your system. Physical definition, synthesizing alternative system components representing a variety of design approaches to implementing the required functions. Having simple, practicable interaction and interfaces among structural subdivisions. Selecting a preferred approach by training off a set of predefined criteria. So again, as I mentioned, you can have multiple technology for each one of these functions, and after that you're going to make up a trade-off analysis and decide which one or which of the technologies you are going to move forward with to attain the best balance among performance, risk, cost, and schedule. Okay, very important, performance, risk, cost, and schedule. I've been talking about performance, cost, and schedule from the beginning of the semester. Now we are incorporating the risk. Risk is also important. Elaborating the design to the necessary level of detail. And then finally, the fourth step is the design validation, designing models of the system environment, logical, mathematical, simulation, and physical. So you're going to be using this to make sure that you don't have to implement every single scenario with the actual system. You can use models and rely on those. Simulating or testing and analyzing system functions against environmental models. Iterating to revise the system model on environmental models, and to revise the system requirements if too stringent for a viable solution until the design requirements are compatible. So sometimes we can shoot for very strict or high requirements, and at the end we cannot get into that performance. So let's say instead of 40 miles per gallon, we were promising 100 miles per gallon. So if we find out that that's not possible, then we can revise the system requirement to find a viable solution for our design. Okay, so here's the system engineering method flow diagram. These are the four parts of the system engineering method, and you see there's some interaction. So you can go from need, requirement, functions, and system model, and then going back, there's some interaction, there's some loops. Also, as we just said, if we end up with some requirements that are too stringent in terms of not being able to meet them, we can go back and revise them. So until we find a viable solution for our model, for our system. Questions? Here's another diagram. This is more elaborate, have more information, but it summarizes what we have discussed as part of this morning lecture. If you follow all the arrows of this diagram, you have a good summary of what we just discussed. So we have the system engineering method, requirement analysis, functional definition, physical definition, and design validation. We can start with a predecessor system. So that's what we have this input here. We have the system model requirements and constraint, development objectives, and inside this box we have organize and analyze inputs, clarify, correct, and quantify. From here we move to the next functional definition. This can be also affected by a predecessor system. We have the functional building blocks. So we translate these requirements into functions, and we define the functions, functional interactions. From there we move again to the physical definition, and finally the design validation. So again, a good summary of what we just discussed. So again, last time or in our previous lecture, we talked about the system life cycle. Now we're talking about the systems engineering method. So what we're trying to do with this table is to compare both. So this is called the system engineering method over the life cycle. And the table is good in terms of understanding how they overlap. So again, we have the stages of the system life cycle at the top, and now we have the steps of the systems engineering method here, and what's inside the table is the discussion on how they overlap. Okay, so again, not necessarily separate. They have, they're targeting the same objective, which is the design of a new system. And you can see the overlapping in this table. And remember, the design of a new system is an iterative process, right? So you remember this spiral model that we discussed. So here is the idea of showing you the system, the spiral model of the system life cycle, and they have also put some those functions or those steps of the system engineering method as part of the spiral model. So this also gives you an idea of how to proceed in terms of designing your system until you get to the production and development. Again, an iterative process meaning that you start with the mission and requirement analysis, move to functional analysis. When you get back to this point, specification and generation, you might need to revise some of the things that you did already in order to meet the requirements, in order to meet that goal. So specification generation, you might need to look at these functional definitions again until you get to the system development and demonstration, and finally the production and development. Okay, so that's the last slide for this